Let's do a titration problem together. So in this titration problem, you've got a couple moving parts where you've got molarity, volume, mass, but then also it's probably something you've never seen before, that of KHP. Doesn't matter. Why do I say it doesn't matter? Well, KHP is something we use in Quant a lot if you want to standardize sodium hydroxide, but you might not have ever seen it before. You've probably seen phenolphthalein though. Remember back in Gen Chem where you guys titrated vinegar? Same concepts. Now first off, two words that I talked about there. Standardize. What does standardize mean? Standardize is simply trying to figure out what is the exact concentration of sodium hydroxide. We're standardizing it. We're saying if I'm going to use this sodium hydroxide solution in other reactions, what's its concentration? Now you might say, well, I measured out the grams and I put it in a volume. Doesn't matter, not for sodium hydroxide. You have to standardize it. Why? Sodium hydroxide is very hygroscopic, so it absorbs water. So even though you weighed 5 grams on a balance, you probably didn't actually weigh 5 grams of sodium hydroxide. You weighed 4 point something grams plus some grams of water. And so you have to figure out what is my actual concentration through a titration, okay? The other thing, KHP, do I actually care what KHP structure is or the formula or the balanced chemical equation? Not really. I just care that it's 1-to-1 because 1-to-1 tells me a lot about how this titration is going to proceed. We know we've got phenolphthalein, so it's going to go from clear to a nice pink color once it's reached the equivalence point. So for this problem, you're given how much KHP you're titrating and then how much titrant is required to achieve that pink color for the equivalence point. All right, so how do we do that? Let's start out with how many grams of KHP we have. So we start out with 0.192 grams of KHP. And let's translate that into moles. Why? Well, we are trying to end up with a final molarity of sodium hydroxide. So we use 0.192 grams of KHP, and how much sodium hydroxide was used to titrate that? Let's put that in liters. So we used 0.0187 liters of sodium hydroxide to achieve that titration. So we've got grams per liters, but we don't have moles. We don't have moles of sodium hydroxide. This is liters of sodium hydroxide, okay, but we're not there yet. And so we need to convert from grams to moles of sodium hydroxide somehow. So how do we do that? We go 1 mole of KHP over how many grams? 204.22 grams. And then, like I said before, 1 mole of KHP is equal to 1 mole of sodium hydroxide. That's all that really matters because now we have moles of sodium hydroxide per liter of sodium hydroxide, and that's going to give us our molarity. So we end up with 0.05004 molar sodium hydroxide. And because we're good chemists, we're not going to standardize sodium hydroxide in 1 trial. We're going to do at least 3. 5 would really be more amazing. But if your 3 trials are really close together, then 3 is sufficient. So in this case, here was our trial A. You'd have to repeat the same step for B and C. So go ahead and stop the video and make sure you've done that for B and C. Now, we are asked to find the average. Remember, average is just add up your 3 trials, divide by 3, or divide by how many trials you have. So in this case, we've got 0.05004 plus 0.05033 plus 0.05138. And all of that is going to divide by 3 to give us our average, which equals 0.05058 molar sodium hydroxide. And that is our final average molarity of sodium hydroxide. But what's my standard deviation? Did I do a good job of making all 3 of my trials consistent? Remember back in Gen Chem where you made bright pink or you made really light pink, and light pink was better. Bright pink meant you missed the endpoint or you added too much of the titrant here. And so by telling and finding a standard deviation, you're able to gauge how well your 3 trials went and if they're going to be precise amongst them. So here is our equation for standard deviation. Now, just to kind of recap in case it's been a while since you've seen this equation, you've got the sum of the individual data points minus the average data point squared divided by n. N is your sample size, which is 3 for this. So there's our equation. Let's do it together just so you can see me working out one of these standard deviations. So standard deviation equals the square root, I'll put the square root sign here in a second, So individual data point, so choose your first data point, 0.05004 minus my average, 0.05058 here, squared. All you're basically doing with standard deviation is saying how far apart are the individual data points from this average, and if that's the average, how far away are we? And so we're basically saying, what's the spread of my data? That's what your standard deviation is telling you. So we've got this value plus, remember it's sum, plus my next data point, 0.05033 minus my average, squared, plus my next data point, 0.5138 minus my average, squared, all over n minus 1, which is going to be 2, and then we take the square root of all of that. That's underneath that giant square root sign to give us a final standard deviation equal to 0.00071 molar. And we'll figure out how we're rounding in our next lecture. Okay, so don't worry too much about how many decimal points I left there. All right, and that is the end. So you should have figured out titrations. We're going from grams to moles to molarity, average, standard deviation, and now you've done a titration problem.